Good morning, all. Welcome to the lecture of complex analysis. Okay, so in last lecture we have seen some examples of our Cauchy residue theorem. Okay, so in previous lecture we have studied what is the Ruchi's theorem, and there are 2 to 3 corollaries depending on the Ruchi's theorem. So today we will see some examples depending on this theorem and corollaries. And we know that what is the Ruchi's theorem. If F and G are two meromorphic functions in a neighborhood of closed disk which is centered at A, having radius will be R, with no zeros or poles on the circle. There is a one circle, that is gamma be a circle which contains all the complex number z, for which modulus of z minus a is exactly equal to some capital R. And if zf and zg denotes the number of zeros of the functions f and g, and pf and pg denotes the number of poles of functions f and g respectively, and they are counted according to their multiplicity along the curve gamma, then modulus of f of z and modulus of f of z plus g of z is less than modulus of f of z plus g of z on a curve gamma, that is circle. Then zf minus zg is nothing but the pf minus pg. That is, the difference between the zeros of the functions f and g is nothing but the difference between the poles of the functions f and g. That one is nothing but the Ruchi's theorem. And after that we have seen some two corollaries. First one is nothing but if f and g are two analytic functions on neighborhood of closed disk which is centered at A, having radius will be R. In Ruchi's theorem, we have to take a meromorphic function. It means either it has no singularity, or if it has a singularity, then it must be pole only, which is from the definition of meromorphic. But here in corollary, we have taken f and g are the analytic. It means it has no singularity. It means number of poles must be equal to 0. And if modulus of f of z plus g of z is less than modulus of f of z, then both the functions f and g have the same number of zeros in this open ball about A of radius R. And in second one also we have to take f and g are the two analytic functions in neighborhood of closed disk which is centered at A and having radius will be R, and modulus of g of z is less than modulus of f of z. Then the two functions f and m plus g have the same number of zeros inside a curve gamma. Okay, now let us see the examples. And again, we know what is the argument principle. Argument principle is nothing but if f is meromorphic on some region G, and p1, p2 up to so on pm are the number of poles, and z1, z2 up to so on zn are the number of zeros of the functions f, and gamma is any closed rectangular curve and which is homologous to 0. It means index of a curve gamma with respect to a point w will be equal to 0 whenever w is a member of C minus G. Then 1 upon 2 pi I integration over the curve gamma f dash of z divided by f of z dz is nothing but summation j running from 1 to n index of a curve gamma with respect to the points zj minus summation j running from 1 to m index of a curve gamma with respect to point poles pj. That one is nothing but the argument principle. And whenever we have to find out the integral value, then we can use this one. So examples. Okay. See now. Evaluate integration over mod z equal to 1 e to the power z minus 2 divided by e to the power z minus of 2z minus 1 dz, and we have to evaluate this integral. Now see the solution. Let us take f of z as and now it is a form of polynomial. Since e raised to z is polynomial, this one is again polynomial. Then this function is analytic on whole complex number system. Is analytic on whole complex number system. As this one is analytic, then it has no singular. It means it has no pole, and f dash of z is now becomes e to the power z derivative e to the power z minus of 2z minus 2, and the derivative of minus 1 will be 0. So here we get this one and we have to evaluate this integral. Now we can easily use our argument principle. So integration over mod z equal to 1, sorry, f dash of z upon f of z, consider f dash z divided by f of z dz is nothing but integration over mod z equal to 1 integration over mod z equal to 1 e to the power z minus 2 divided by e to the power z minus of 2z minus of 1 dz. Now by argument principle, this one is nothing but by argument principle, this value is equals to 2 pi I into this one is now argument principle is nothing but 1 upon 2 pi integration over mod z equal to 1 f dash of z divided by f of z dz is nothing but summation over j running from 1 to n number of zeros, that is actually it is nothing but the number of zeros minus number of poles. As here function is analytic, it means it has no pole, so that part will be 0 into number of zeros of the function f inside the curve mod z equal to 1, inside mod z equal to 1. Okay, now as f of z is equal to e to the power z minus of 2z minus of 1. Sorry, f will be taken this one. Now here we will take f dash f1 as minus of 2z and g1 as e to the power z minus of 1. Now, which implies modulus of f1 is equal to minus of 2 and which is equal to 2, and modulus of g1 which is nothing but e to the power z minus of 1. It can be written as integration over integration from 0 to z e to the power z minus 1 dz. Sorry, e to the power some u into some du. Okay, since whenever we will find out this integral, then we get e to the power u as it is, and whenever we will put the limits, then we get e to the power z minus 1. But here mod z will be equal to 1, then 0 to 1 e to the power u du. Okay, so this will be nothing but some e minus 1, and value of u will be 2 point something minus 1. It is some 1 point something, that is it must be less than 2, which implies modulus of g1 is less than modulus of f1. Then by the last corollary of Rouché's theorem, as modulus of g1 is less than modulus of f1, then f1 and f1 plus g1 have the same number of zeros, which implies by Rouché's second corollary, f1 and f1 plus g1 have the same number of zeros. Same number of zeros inside mod z equal to 1. Since here we have using mod z equal to 1. Okay, so the two functions f1 and f1 plus g1 have the same number of zeros inside this curve, but f1 plus g1 is nothing but addition of these two. f1 is this one, g1 is this one, addition of these two is nothing but f of z, which implies f of z has same number of zeros inside the curve mod z equal to 1. Now f1 and f1 plus g1 have the same number of zeros inside mod z equal to 1, but f of z is not, but f1 of z is nothing but f1 of z is nothing but minus of 2z, and curve will be modulus of z will be equal to 1. It means this will be a circle having radius will be 1, and here will be center 0. This function has only one 0, minus of 2z equal to 0, which implies z equal to 0. So z equal to 0 is a 0 of this function f1 of z, which implies f1 has only one zero inside mod z equal to 1. But f1 and f1 plus g1 have the same number of zeros inside the curve mod z equal to 1. It means f1 plus g1 has 1 0 inside modulus of z equal to 1. But f1 plus g1 is nothing but our f. So f has 1 0 inside mod z equal to 1. Okay, so in this way we can find out. Now here there is only 1 0 for the function f of z under this modulus of z equal to 1. So put that value here. So we get integration over modulus of z equal to 1 e to the power z minus 2 divided by e to the power z minus 2z minus 1 dz is nothing but 2 pi I into 1, which is equal to 2 pi I. Okay, so in this way we can use our Ruchi theorem and argument principle in for solving examples. Now take one more example. Second, integration over modulus of z equal to 1 by 2 z square minus 2 divided by z cube minus of 6z plus 8 dz. Okay, solve this one. Solution. Let f of z is nothing but z cube minus of 6z plus 8. As it is a polynomial, so it is analytic on whole complex number system. On complex number system. And f dash z is now becomes 3z square minus of 6 plus 0. This can be written as 3 into z square minus of 2. Okay. Now write, consider modulus of z equal to 1 upon 2 f dash z divided by, this can be written as that is z square minus 2 divided by z raised to 3 minus of 6z plus 8. It can be written as 1 upon 3 integration over modulus of z equal to 1 upon 2 f of f dash of z divided by f of z tz. Sorry, tz. Since f of z is as it is z cube minus 6z plus 8, f dash of z is nothing but 3 into z square minus 2. But 3 get cancelled, then we get z square minus 2. So this will be equal to this one. Now by Ruchi's theorem, this one is nothing but 1 upon 3 into 2 pi I into, as f is analytic, then it has no singular point. It means by argument principle, value of this one is nothing but 2 pi I into it's a number of zeros under this mod z equal to 1 by 2. Number of zeros of f inside modulus of z equal to 1 upon 2. Okay, so which is nothing but 2 pi I into 2 pi I divided by 3 into number of zeros. Here f of z is nothing but z cube minus of 6z plus of 8. Take f1 as, take f1 is equal to z cube and f2 or f2 is equal to minus of 6z plus 8, and find out its modulus. Since here we have to use the Ruchi's theorem. Modulus of f1 equal to modulus of, here curve will be mod z equal to 8. It means this will be a curve. Sorry, mod z equal to 1 by 2. So this will be a curve with circle 1 by 2, which is centered at 0. Okay, as this will be a circle having radius will be 1 by 2, and we have to find out the modulus over this circle. It means here value of z will be 1 by 2, 1 upon 2 cube, which is nothing but sum 1 by 8, and modulus of f2 is equal to modulus of minus of 6z plus 8, which is nothing but modulus of 6z plus 8, which is nothing but 6 divided by 1 by 2 plus 8. which is equal to 3 plus 8 and which is equal to 11, which implies modulus of f1 is less than modulus of f2 since 11 is greater than 1 by 8. Okay, as f1 is less than modulus of f1 is less than modulus of f2, then by Ruchi's theorem, by Ruchi's second corollary, second corollary, both f1 and sorry f2, f1 is less than f2, it means f2 and f1 plus f2 have the same number of zeros, same number of zeros inside mod z equal to 1 by 2. But f1 plus f2 is nothing but our f. Okay, which implies now here modulus of z equal to this will be 1 by 2. And what is the value of f2 here? F2 is nothing but minus of 6z plus 8, which is equal to 0, which implies minus of 6z is equal to minus 8. It means z equal to 8 upon 6. 8 upon 6 is equal to 1 point here 2, 1.3 something, but with this will have 1 by 2 is nothing but some 0.5. So f2 has 1 0, that is 8 divided by 6, and which is in outside this circle. Since here circle will be of radius 1 by 2, it means 1.3 is obviously greater than 0.5, it means it is outside a circle. Therefore f2 has no 0 inside this modulus, which implies f2 has no 0 inside mod z equal to 1 by 2, since f2 has a 0 but which is a outside this curve. But we know that f2 and f1 plus f2 have the same number of zeros inside mod z equal to 1 by 2, but f2 has no 0 inside mod z equal to 1 by 2, which implies f1 plus f2 has no 0 inside modulus of z equal to 1 by 2. But f1 plus f2 is nothing but f has no 0 inside modulus of z equal to 1 by 2. As it has no 0, then its value will be 0. So put here the value 2 pi I into 0, and which is equal to 0. So integral over the curve gamma z square minus 2 divided by z cube minus 6z plus 8 dz is equal to 0. Okay, so in this way we can solve our problems. Now the next concept, which is nothing but spaces of analytic spaces of analytic functions. Now, let G be any open subset of complex number system. Let capital G be any subset of complex number system. C from G to C of G, C be the space of all continuous functions, continuous functions from G into C. Okay, so here we have taken capital G be any subset of C, and C of GC denote the all the continuous functions from this set G to complex number system, and clearly the C of GC is a vector space over the complex number system, and C of GC, that is the space of all the continuous functions from G to C, is a vector space over the field C, is a vector space over C. Okay, and H of G denotes, and capital H of G be the space for be the space for all continuous functions, sorry, all analytic functions. All continuous functions from G to C is nothing but this set C of GC, and H of G or H of C, H of G is nothing but the space of all the analytic functions on this set G. All the analytic functions on G. Okay, so whenever G be any subset of C, then the space which contains all the analytic functions on set G is nothing but H of G. Okay, remember this. This will be useful in next theorem. Now, there is one theorem which is nothing but a Hurwitz's theorem. See what is a Hurwitz's theorem. Hurwitz's theorem. Statement: let capital G be a region. Let capital G be a region, and suppose the sequence Fn Fn in H of G converges to a function f if f is non-zero and a closed disk which is centered at A having radius small r, sorry, capital R, will be a subset of G, and f of z is not equal to 0 for modulus of z minus A equal to R, then there is an integer capital N such that for small n greater equal by this capital N, and then we have to find out then f and fn have the same number of zeros, have the same number of zeros inside open ball about A of radius. Okay, so this will be a statement for our Hurwitz theorem. What is the Hurwitz theorem? It give you any region, and suppose there is one sequence Fn in H of G, where H of G is the space of all the analytic functions on G, and which converges to F. It means it is clearly that Fn converges uniformly to a function F, and whenever F is not equal to 0 and the closure of A is the subset of G, and F of Z is not equal to 0 on the boundary points of that circle, then there is one capital L any integer for which whenever we will take small n will be any member which is greater equal by n, then f and fn have the same number of zeros in open ball about A of radius r. That is, here just we have to use the definition of uniform continuity. See the proof then. So here f is not equal to 0 and b closure of, that is closed disk which is centered at A cap, radius will be capital R, will be a subset of G, and f of z is non-zero on this circle modulus of z minus A equal to capital R. So let us take delta as define the say delta which contains minimum of modulus of f of z whenever modulus of z minus A is equal to R. That is, here we have to take all the functions f of z and its modulus which are belonging to this on the boundary of this circle. As here f of z is not equal to 0 on this boundary, it means f of modulus of f of z is never equal to 0. As it is a mod, then it must be greater equal by 0, and it is never equal to 0, it means it is obviously greater than 0 only. Whenever we will take the minimum of greater equal values, greater than values 0, then obviously that minimum is also greater than 0 only. So it means delta will be greater than 0. So delta is greater than 0. As Fn converges to F uniformly, Fn converges to F uniformly. Then by the definition of uniform continuity on modulus of z minus a equal to r. Therefore, for some delta less than delta greater than 0, therefore for delta upon 2 greater than 0, there is an integer, there is an integer capital N such that for all small n greater equal by capital N, modulus of f of z minus fn of z is less than modulus of f of z. Okay. First x it is less equal by some our modulus of f of z minus of is less than some delta upon 2, which is obviously less than delta, but delta is nothing but f of z, so which is must be delta is a minimum of modulus of f of z, then obviously delta is strictly less than mod f of z. Okay, since delta is nothing but the minimum value of modulus of f of z, so obviously it is less equal by modulus of f of z, which implies f of z minus fn of z is less than. Now, by the second corollary of Cauchy's theorem, if f and g are the two analytic functions and modulus of f of z plus g of z is less than modulus of f of z, then both the functions f and g have the same number of zeros. Here f is nothing but f only and g is nothing but this fn. Then by second, by first corollary of Cauchy's theorem, its theorem, f and fn have the same number of zeros, same number of zeros inside this open one, and hence the. Okay, that is we have to. Okay, now the next theorem, which is nothing but the squad's lemma. Now there are 2 to 3 theorems. After that, our chapter will be finished. Now here we will see some only the statements of these 2 to 3 theorems. That is squad's lemma, Monte theorem, and Weierstrass factorization theorem. Okay, and after that, our chapter will be finished. Okay, let's see the statements only. Let theta, sorry, say D is nothing but it contains all the z belonging to K. Sorry. Let theta be a set which contains all the complex number z for which mod z will be equal to 1. Sorry, modulus of z is strictly less than 1. Be the open unit, be the open unit disk, and f is analytic on this set theta, analytic on this theta, such that first one, modulus of f of z is less equal by 1 for all z belonging to this symbol theta. This symbol will be some like similar to our theta. And second one is nothing but f of 0 is equal to 0. Then we have to prove that modulus of f dash 0 is less equal by 1 and modulus of f of z is less equal by mod z for all z belonging to our corresponding set theta. Moreover, if modulus of f dash of 0 will be equal to 1, or if modulus of f of z is equal to mod z for some z not equal to 0, or some z not equal to 0, then there is a constant c. There is a constant capital C such that modulus of C will be equal to 1, and modulus of f of w will be equal to this C into w, where w will be equal to, for w belonging to this theta. Okay, so this will be a square's lemma. Whenever theta will be a set which contains all the complex numbers z such that modulus of z will be less than 1, which is the open unit disk. Open unit disk means its center will be 0 and radius will be 1, and it is analytic on this corresponding set theta. That is, f is a function which is analytic on theta. Then modulus of f of z is less equal by 1 and f of 0 equal to 0. Then we have to prove that modulus of f dash of 0 is less equal by 1, and modulus of f of z is less equal by mod z for all the z belonging to this corresponding sets theta. And whenever we have modulus of f dash of 0 equal to 1, or modulus of f of z will be equal to mod z for some non-zero complex number z, then there exists one complex number c such that modulus of c will be equal to 1, and f of w is nothing but c into w, where w is a member of theta. This will be our square's lemma. Now there is one definition which is nothing but the locally bounded set in h of g, where h of g is the set of all the analytic functions on g. Let us see what is a locally bounded set in h of g. Locally bounded set in h of g. A set f which is subset of h of g is locally bounded if for each point a in g, each point a in capital G, there are constants m, there are constants capital M and capital small r greater than 0, such that modulus of f of z is less equal by this m. That is, means f is a bounded function for all z with modulus of z minus a less than this small r, and for f belonging to this curly f, that is, this will be a curly f, belonging to this f. Okay, so that will be a local bounded set. Whenever f is any subset of h of g is local, and it is said to be locally bounded if for each point a in g there are constants capital M and small r greater than 0, such that modulus of f of z is less equal by this m. It means this will be a function which is bounded by this m for all z with modulus of z minus a less than this small r for any small f belonging to this our set f. Okay, so this will be a definition for our locally bounded set in h of g. There is one more definition. That one is nothing but normals. See what is a normal set. Okay, what is a normal family? Normal family. Okay, So any family is said to be a normal. A family F, which is subset of H of G, that is subset of all the quadratic functions on G, is called normal. Is called normal whenever, that is if each sequence in F has a subsequence has a subsequence which converges in H of G, which converges in H of G. So any family F which is subset of our set of all the analytic functions on G is called a normal family if each sequence in this F has one subsequence which converges in this H of G. Then we say that the corresponding family will be a normal family. Now depending on these two definitions, there is one theorem which is called as a Monte theorem. Monte theorem. Okay. See what is the statement for Monte theorem. A family F in H of G is normal if and only if F is locally bounded. Okay, so this will be a theorem for our Monte theorem. So any family F in H of G is normal if and only if it is locally bounded, and we know that what is a normal family and what is a locally bounded set. Okay, so depending on these two definitions, this will be an one important theorem. Now there is one more theorem which is nothing but the Weierstrass factorization theorem. See its statement. Weierstrass factorization theorem. See what is a Weierstrass factorization theorem. Let f be an entire function. Let small f be an entire function, and let a and b non-zero, sorry, and a and b are non-zero zeros. Non-zero zeros means which are exactly not equal to zero, but they are the zeros of the function f of f repeated according to their multiplicity, according to multiplicity. And suppose f, so small f has a zero at z equal to 0 of order m greater than 0 or get equal by 0, then there is an entire function small g and a sequence of integers pn such that f of z is nothing but z raised to m into e to the power g of z into, this will be a multiplication for symbol n running from 1 to infinity epn z upon e. Okay, so this will be a Weierstrass factorization theorem. What is its statement? If f is any entire function, it means it has analytic on whole complex plane, and a and b are non-zero zeros of f. They are the zeros of function f but not equal to 0. and they are repeated according to their multiplicity. And suppose f has one 0 at point z equal to 0, and which is of order m, and where m is greater equal by 0, then there is an entire function small g and a sequence of integers pn such that f of z is in this form, that is z raised to m into e to the power z into multiplication of all these values, that is epn into z upon n. So this will be a Weierstrass factorization theorem. Now the last theorem of our last unit, which is nothing but the Goodsall theorem. See its statement only. Let capital G be a open set. This will be an important theorem. Let capital G be a open set and f is a function from G to C be a differentiable function, then f is analytic on G. Analytic on set G, which is nothing but the Goodsall's theorem. Okay, this will be used. This can be proved by using the Morera's theorem. This will be an important result. That is, if G be any open set and f from G to C be an differentiable function, then f is analytic on G. Okay, so this will be a last point of our fourth unit. Here our syllabus will be completed. Okay, thank you for watching the lecture.